Hello and welcome back to a new video. In this video I'll introduce the idea of tangent spaces of a Euclidean or pseudo-Euclidean space. This concept, because of the flat structure of a Euclidean space, at first glance seems to be unnecessary, trivial or superfluous. Nevertheless, its generalizations to non-Euclidean cases and to surfaces proves to be of crucial importance for the development of a mathematical arsenal suitable to describe the futures of these structures. The idea of the tangent spaces of RO3 comes from the notation of tangent vectors of a curve. A curve C of the space RO3 is a subset of RO3 whose points are determined by a differentiable function of the form C I that contains an element T maps X subscript T is equal to, by definition, X of T is equal to X1 of T, X2 of T, X3 of T. Sorry, which is an element of RO3. And these are just indices, so they're not powers, just to make a note. And the domain of the parameter T is an interval I of the real numbers R. The curve C is well defined under two assumptions. Well, A, that we accept the constant function, which maps the whole I at one point, or actually one fixed point of RO3, is a degenerated curve. We call it the constant curve. And B, that for any curve different of the constant curve, we assume that for any T, an element of I, there is an index J, an element of the set 1, 2, 3, for which it holds that X dot J of T is equal to derivative of Xj of T with respect to T is not equal to 0. And that is that the tangent vector of a curve is nowhere identical with 0. The tangent vector of the curve C at its points P equals P X of T, determined by the triple X equals XT, is defined by the derivative XT, or actually X dot T equals X dot of T is by definition equal to the derivative with respect to T of X1 T, X2 T, X3 T. And we make the parameter transformation T equals lambda capital T, where lambda is, well, a constant, which is an element of R, the real numbers. And the new parameter capital T runs the interval, well, I bar, a subset of R. And the abstract point P of the curve C is represented by the identical triples X bar of capital T and X of T. And X bar of capital T is equal to X of T is equal to X of lambda T. The tangent vector of the curve C at point P as a function of the parameter of capital T is calculated by the derivative T dx bar of capital T with respect to d capital T equals dx of t with respect to capital T equals dx of t with respect to t times dt with respect to capital T equals x dot of t times lambda. And we can apply that every vector, say sigma, is equal to x dot of t lambda, where lambda is an element of R, is a tangent of the curve C at its point Px of t, or else every element of the one-dimensional vector space, say L of the set of x dot t generated by the vector x dot t is a tangent vector of the curve C. Let us now consider a point P equal to Px, an element of R03, determined by the triple x, and assume all the curves of R03 that pass by P. Well, we define the set Tx R03 of all the vectors sigma of x, which are tangent to some curve of R03 passing by P, and sigma of x is an element of Tx R03 if and only if, by definition, there is some curve Cx xt is equal to x of t in R03 with, well, x of 0 equal to x and sigma of x equal to x dot of 0, or Tx R03 equals the set of sigma of x such that sigma of x is tangent vector at x of a curve in R03 passing by x. We symbolize sigma j of x, where j is equal to 1, 2, or 3, the Cartesian coordinates of the vector sigma x, and that is tangent at the point x to a curve of R03 passing by x. And we may make a proposition, namely that the set Tx R03 is a vector space isomorphic to the R-dimensional Euclidean space. It is called the tangent space of R03 at the point x of the space. I may prove it, so our first step is that any tangent space Tx R03 contains the zero vector, that is, the tangent vector of the degenerate constant curve Cj of t equals xj is the zero triple 000. Then B, let sigma of, well, x equal xj times sigma j of x, an element of tangent space. And then, according to the definition of tangent spaces, there is a curve xtj equal to xj of t, such that xj of 0 is equal to xj, and x dot j of 0 equals sigma j of x. We shall show that for any gamma an element of R, it holds that sigma of x times lambda is an element of the tangent space. And we have that for gamma equal to 0, it holds. Anything times 0 is equal to 0. And then according to A, well, sigma x times lambda is an element of the tangent space. So that holds. And then for lambda not equal to 0, define the curve x bar tj equal to x bar j of t equals xj lambda t. And this curve passes through x, so x bar j of 0 is equal to xj of 0 equals xj. And hence, by definition, its tangent vector at t equals 0 belongs to the tangent space. So we can conclude that tx, or of 3, has an element dx bar of t with respect to t at t equals 0 is equal to dx of lambda t with respect to t at t equals 0 is equal to dx of capital T with respect to capital T at capital T equals 0 for lambda equal to sigma x times lambda. And then C, let sigma 1 of x equal xj times sigma 1j of x, and then same for the other indices, namely that sigma 2 of x is equal to xj times sigma 2j of x. I just write like that for index 2, an element of the tangent space.